Hello. This lecture will be on the equilibrium of moving things. You have the handout attached into your notebook, and you're going to add additional annotations onto your note page. This is the first slide of the notes. So we have equilibrium is a state of no change with no net force acting on it. So there are two general types of equilibrium: static and dynamic. All right, so I'm going to take a moment and highlight here for you those two. So we have static equilibrium and we have dynamic equilibrium. Now, another word for static would be still. Okay, so static is still, meaning that it's not moving and it's at rest. Dynamic equilibrium is moving equilibrium. An example of something then is in static equilibrium would be any object at rest. And the example used here is a hockey puck at rest on slippery ice. An example of dynamic equilibrium would be any object that is moving and specifically at a constant speed in a singular direction. So in other words, it's not turning. Okay, so constant speed and not turning would be something in dynamic equilibrium. Okay. Next slide. Equilibrium test. Whether something undergoes a change in motion. For example, a crate at rest is in static equilibrium. There's no change in its motion. Example, when it's pushed at a steady speed, it is in dynamic equilibrium and there's no change in motion. So an object can be in two different types of equilibrium again, static and dynamic. Static is when there's no motion, and dynamic is when there is motion, but it's a constant type of motion, meaning the same speed in the same direction. It's not speeding up, slowing down, or turning. All right, first check question. A bowling ball is in equilibrium when it is at rest, moves steadily in a straight line path, both of the above or none of the above. So going back to our definitions of equilibrium, static, it is when there is a state of no change with no net force acting on it. So in other words, we're not changing our motion. So if something is at rest, it is in equilibrium. Specifically, it's in static equilibrium. If something is moving steadily, this means moving steadily means constant speed. Okay, so constant speed. Let's see if I can write this with this. Oh, that's going to be bad. Okay. I should definitely be recording this with my iPad and not my computer. Okay. Oh, that's horrible. All right. Well, never mind on that. Constant speed. So both of those are in equilibrium. At rest, that would be static equilibrium. Steady pace in a straight line path, that would be dynamic equilibrium. So the correct answer is C, both of. All right, so on your Go Formative, you're going to answer the correct answer here, and you're going to explain that answer here based on what I just described for you. All right, next question check. Equilibrium moving things. You push a crate at a steady speed in a straight line. If the friction force is 75 newtons, how much force must you apply? If you recall from our force and motion lab, we had the little stick figure guy and he would have to push the skateboard or the crate. Anytime he pushed to the right and there was friction, there was a friction force to the left. And so this brings us back to the whole concept of balanced and unbalanced forces. So we know that So let me see here. No. No, we'll just try it. I'll just try to draw it. Okay. So balanced and unbalanced forces. We know that if we have a certain number of newtons to the right and a certain number of newtons to the left, if it's the same value, then the total force is zero. The net force is zero. So anytime we want something to be in equilibrium, it needs to have a net force of zero. So if we apply a force of, if there's a friction force of 75, then to have the counter force would have to be, we want the total to be zero. Okay, so backing that up one more time. For something to be in equilibrium, it needs to have a net force of zero. And we talked about that in a prior lecture, how when net force is equal to zero, we also identify that as a state of equilibrium, and there's no change in the motion. So if we push it in a straight line at a steady speed and the friction is 75, then the force you apply must be exactly 75 as well. Okay. The moving Earth. Copernicus proposed that Earth was moving, circulating the sun. This idea was refuted by people. For example, if the Earth moved, how could a bird swoop from a branch to catch a worm? Solution: as it swoops due to inertia, it continues to move sideways at the speed of Earth along with the tree, the worm, etc. So people initially argued that the Earth could not be moving because if it was, as soon as the bird left the tree branch, the tree would speed away from it and leave the bird behind. But the bird always stays with the tree. And that's something that maybe back then was difficult to kind of visualize in their mind because they didn't have fast moving vehicles to make this other observation. But if you want to think about being inside a car, okay, or a train or an airplane, you are going the same speed as the plane. If you stand up in the plane, you don't suddenly get slammed to the back of the plane because the plane has inertia and is moving at a specific speed. You have inertia and you're moving at a specific speed, same as the airplane. Now, if you apply force to your feet on the ground, you can make yourself go towards the front of the plane or towards the back of the plane, essentially going a different speed than the plane itself. But your perspective is inside the plane. So it seems like everything's normal, just as if you were just sitting on Earth. So imagine that the airplane is actually the Earth moving through space, and you're just you on Earth, same as before. So if you throw something straight up in the air while you're standing on Earth's surface, it comes right back down to you because both you, the Earth, the object you're throwing is all moving together. In the same sense, if you're on an airplane and you toss something into the air, straight up into the air, it's going to come right back down to you. It's not going to slam into your face as you keep moving with the airplane. The object will also move with you because it has inertia as well. Okay, so where would the coin land? Well, it would just land straight back in your lap, which is why you can do that. If you've never been in an airplane, you've been in a car. So if you toss something straight up in the air, it's going to come right back down into your lap. It's not going to whoosh past your head. Now, this last question here is, let's take a look at it. It says, what is the downward force that is missing? The plank is in static equilibrium. Okay, so number one, anytime something is in static equilibrium or dynamic equilibrium, we know that the summation of the forces or the net force is equal to zero. Okay, so that means that we know that if we add up all of these vector arrows, these force arrows, that they should equal zero because it is in a state of equilibrium, whether it's static or dynamic. In this case, static. So to start with, upwards, we have 400 and we have 400. So we have two 400 Newton forces pointing upward. Okay, so we have 400 plus 400 equals 800. So upward, we have 800 newtons. Now, we know that our net force is supposed to be 0 because we're in equilibrium or static equilibrium. So that means that downward, we should also have 800 newtons. Otherwise, we would not have a balanced force here. We would not have equilibrium. The mass or the weight of the man standing on the scaffolding here is 500 newtons. So the question we ask is, if he's 500 newtons, plus what equals 800? Okay, so we have to have an equal upward and downward force to be in equilibrium, to have that net force equal 0. So if we have upward 800, downward 500 plus unknown equals 800, then our unknown amount has to be 300. So the missing value is 300 newtons. Now, it doesn't matter if you completely understand the situation that we're looking at here, but just the bare facts that the upward forces total to 800, therefore the downward must total to 800, and we're trying to find the missing amount. What is the missing amount of force that we don't see labeled on this picture? All right, make sure on your handout you've labeled and annotated the notes as I was going through that lecture. Make sure you answer and submit the Go formative as well. Additionally, there are some questions to answer in your notebook as assignment number 17, and that is to be done today as well. And thank you.